next parts of our examples here, we're going to look at definite integrals using our trig substitution. So example 5, we're going to integrate from 0 to 3 radical 3 over 2. We have x squared over the binomial 1 minus x squared raised to the 3/2 power. So let's rewrite that so we know what's inside my square root symbol here. So that's the square root of 1 minus x squared all to the 3rd power. So that denominator of 2, that's my square root. So here, 1 minus x squared, 1 is going to be my hypotenuse. My x is going to be opposite of theta. And my square root of 1 minus x squared will be my other leg. All right, so looking at what we have here, based on my theta, you want x on the top over 1. That's going to be sine of theta is going to be equal to x. So it's already solved for x. Just take your derivative of both sides. We'll get dx equals cosine theta of d theta. All right, next, what we could do is save ourselves a little bit of time. And that instead of doing the trig substitution and substituting back in the algebra and then evaluating it, let's just change our lower bound and our upper bound in terms of theta, and then we'll just integrate with respect to theta, plug in our values, and be done. So when x is equal to 0, sine of theta equals 0. That means, all right, theta has to be equal to 0. When x is equal to 3/2, when does sine of theta equal 3/2? That's when theta is equal to pi over 3. Again, you see that radical 3 over 2, you're thinking of that 30, 60, 90 right triangle, opposite over hypotenuse, so that's the 60 degrees, just rewriting it in radians. So rewrite my integral from 0 to pi over 3. X squared is going to be sine squared. X squared sine squared theta dx cosine theta d theta. Well, I can see right here I'm going to have 1 minus sine squared theta is going to be cosine squared theta. Taking the square root of that will cancel out the squared. And so this will be cosine theta cubed in my denominator. Then this cosine theta with the d theta can cancel this cosine cubed theta and make it cosine squared theta, which in turn we now have tangent squared theta using your quotient identity. So we'll switch out our tangent squared theta. I think we saw this before. We got to change that out to secant squared theta minus 1. And now we can integrate secant squared theta. That's going to be my tangent of theta. Integrate your 1. That's going to be theta. We'll put in pi over 3 for the thetas minus the zeros. And I'm almost positive we did this back in the powers to tangents and secants. And we're going to get 0 for this tangent of 0. Tangent of pi over 3. That's the square root of 3 minus pi over 3. Example 6, now we have a little bit of a dilemma. Here's my square root, but I don't have a perfect square value here. So what we'll do is we'll complete the square of what we have inside of our square root symbol so we can use our trig substitution. So off to the side, I'm going to mess with this 2x minus x squared. Now, in order to complete the square, your x squared has to be positive, so I'm going to factor out a negative. And then to complete the square, I want to turn this x squared minus 2x into a trinomial that I can factor. So I'm going to add something and subtract the same thing inside my parentheses. So to find what I want to add is you take that minus 2x, divide it by 2 is negative 1, and square it to get a 1. So this plus 1 is what I want to add, but to keep it the same value, I also have to subtract 1. So this trinomial right here is going to factor to x minus 1 squared, and this minus 1 will sit right here. Now we can distribute the minus sign back in to give us 1 minus, and here's our variable squared. It's just going to act as a binomial squared. So we're going to substitute this into my square root symbol, and now we'll build our right triangle. So it's 1 minus, which means 1 is the hypotenuse. The square root of the binomial squared x minus 1, that will be across from my theta. And the entire square root here will be on this leg. Now, option here, if you want to use this square root right here, that's fine when we substitute back in our algebra. So these two are optionals to use. So building my trig function will be the sine of theta is equal to x minus 1 over 1. Well, we don't need the 1 in the denominator. Sine of theta is equal to x minus 1. Step 3, we got to solve for x, so just add over the 1. So instead of saying sine of theta plus 1 equals x, I'm going to switch it around so I can now take the derivative of both sides. That will be dx, and the derivative of sine theta is cosine theta d theta. So now we're ready to substitute back into our integral. So this x up here, whoops, I'm looking at the wrong one, right here. This x will be sine of theta plus 1, and then we're going to put sine of theta plus 1 for this x, and on the side we'll have cosine theta d theta. So there's my substitution. So the nice thing here is inside this set of parentheses, the plus 1, minus 1, they're going to cancel out. So let's scratch that out. It's not there. And I now have 1 minus sine squared theta, which again is cosine squared theta. And then take the square root is going to give me just a cosine. And that cosine will cancel with this cosine theta. So I'm left with sine theta plus 1 d theta. So we can integrate sine of theta, that's negative cosine theta. Integrate the 1 as theta plus your constant. And now we'll convert this back into algebra. We do have a theta here, so again, remember, you have to go to where x is equal to your trig function, and we need to solve that for theta, so subtract over the 1. Take the inverse sine of both sides. There's my theta value. So that's going to replace this theta, and cosine of theta is going to be this square root over 1, or you can use this one instead because they are equivalent. So I'm going to opt with this, but I think I'm going to switch it back for my final answer. You can have negative the square root of 2x minus x squared. That's just easier to type into WebAssign, plus the inverse sine of x minus 1 plus c. Example 7, we have another square root that we don't have perfect squares in here. So again, off to the side, we're going to complete the square. So here, again, look at just the x squared minus 6x. The 13 is not allowing us to factor this. So to find a perfect square, you take half of negative 6, which is negative 3. You square it, and that's 9. But then you also got to subtract the 9 to cancel that out. So block off this trinomial here. This should turn into a binomial squared, so x minus 3 squared. What two factors multiply to be 9 and add up to be negative 6? X minus 3, x minus 3. Negative 9 plus 4 is 13, so here's my perfect square. Here's my perfect square. We'll rewrite our integral with that radicand on the inside. So we're adding the two perfect squares, which means this whole square root, that's my hypotenuse. And so again, across from theta, you're going to want to put your x minus 3, and we'll put the square root of 4, which is 2, on this leg. So looking at these two sides, this is going to be tangent of theta equals x minus 3 over 2. We want to solve for x, so multiply the 2 to the tangent, then add over the 3. So x equals 2 tangent theta plus 3. Take the derivative of both sides, so dx equals 2 secant squared theta d theta. The derivative of 3 is just 0, so that kind of cancels away. So now, looking at my new integral here, we're ready to substitute in. 2 tangent theta plus 3 goes in for x. You can see the plus 3 and minus 3 will cancel out. My dx was replaced with 2 secant squared theta d theta. So canceling my 3's. Let's rewrite this integral over here. Let's square the 2 and make it a 4 tangent squared theta plus the 4. Factor out the 4. We get the binomial tangent squared theta plus 1, which is a Pythagorean identity for secant squared theta. We can take the square root of that, and now we get 2 secant theta in our denominator. Well, the 2 cancel, the secant theta cancels with one of these, so it simplifies our integral down to secant theta d theta. Integrating that, that's the natural log of the absolute value of secant theta plus tangent theta plus a c1. Remember, every time you get one of these natural logs, and we're going to have these fractions going back in, we're going to be able to use that quotient rule and hopefully factor out a positive, factor out a natural log of some positive value, which is a constant. So secant theta, that's going to be my hypotenuse over the 2. Now, instead of writing all this, I'm opting to go back to the original trinomial. It's 6 of one, half dozen of the other. It doesn't matter. Tangent of theta, I already have that, x minus 3 over 2. They do have common denominators, so we're going to add that together. And again, here's where we use our quotient rule for logs. The natural log of the absolute value of the top minus the natural log of the absolute value of the 2, which becomes part of my constant, and that's my final answer. And that wraps up our section 8.3.